There is something deeply wrong with modern construction. In 1986, a historic cabin in Wisconsin, built in 1847, was measured during a brutal winter night. Outside temperature, -38 degrees Fahrenheit. Inside, with just a small fire in the hearth, the temperature held steady at a comfortable 68 degrees. The walls are not insulated with foam or fiberglass. There is no furnace, no forced air, no double-pane windows. Then there is the modern home, built with all the latest technology, stuffed with insulation, equipped with a $20,000 HVAC system. Yet when the power goes out during a winter storm, these homes drop to freezing in just hours. Pipes burst, families huddle under blankets, the house becomes uninhabitable. This gets researchers asking, how did Viking builders, with nothing but axes and hand tools, create structures that maintain warmth in conditions that would kill a modern family? What do they know that we have forgotten? The answer is not just about thick logs. It is a complete system of thermal mass, air management, and strategic heating that works with the physics of heat, not against it. Today, we investigate the forgotten construction secrets that turned a simple log cabin into a fortress of warmth. Before we dive in, drop a comment and tell us, have you ever lost heat in your home during a winter storm? How long does it take for your house to become uncomfortably cold? Let us know below. Section 1. The Modern Failure. A House of Cards Against the Cold. Walk into any modern home during winter, and you feel the evidence of a fundamental problem, that constant hum of the furnace, cycling every 15 minutes, the uneven temperatures. Walk near a window and feel that cold draft. Modern construction is built on a flawed premise. We can overcome the cold with brute force. The result is a house completely dependent on continuous energy input. The moment that stops, the house begins its rapid descent toward outside temperatures. The numbers are startling. The average modern American home loses approximately 1 degree Fahrenheit per hour during a power outage when outside temperature is around freezing. In a severe cold snap at -10 degrees, that rate doubles. Within 12 hours, a modern home reaches dangerous temperatures. Why? The problem is thermal mass, or rather, the complete lack of it. Modern homes are built with thin materials, 2x6 studs with insulation, half-inch drywall, thin siding. These materials slow heat transfer but do not store heat. They have almost no thermal capacity. Think of it like this. Insulation is like a thin windbreaker. It blocks wind, but the moment you stop generating body heat, you get cold fast. Thermal mass is like a thick wool coat warmed by a fire. Even after you step away, that coat keeps radiating warmth for hours. And there is another problem: air infiltration. Despite all the house wrap and vapor barriers, the average new home has the equivalent of a 2-foot by 2-foot hole in the building envelope. Your furnace is not heating your home. It is heating the outdoors. Compare this to surviving Viking log structures in Scandinavia and Russia. During multi-day blizzards at -40 degrees, these cabins maintain livable interior temperatures of 50 to 60 degrees with only a single fire per day. Some stay above freezing for over 72 hours with no fire at all. This is not magic, this is physics, applied with brutal efficiency. If you are finding value in this investigation, hit that like button and subscribe. It helps us share this forgotten knowledge with more people questioning why modern solutions keep failing us. Section 2. The Investigation: Clues from the Forest. To understand the Viking log cabin, we start where they start, in the forest. The choice of tree is not random, it is the foundation of everything. In Scandinavia and northern Russia, builders seek out old-growth pine and spruce, at least 80 to 100 years old, growing slowly in harsh, cold climates. These trees have incredible density. When dendrochronologists examine timbers from Viking Scandinavian structures, they find rings so tight you can barely see them. Some sections show over 100 rings per inch. Modern plantation timber? Just 10 to 20 rings per inch. That density difference is everything. Dense wood has more mass per cubic foot. More mass means more heat storage capacity. A single 12-inch diameter pine log from an old-growth tree weighs over 60 pounds per linear foot. The same size modern lumber, maybe 35 pounds. That extra mass is thermal capacity locked into the walls. But logs alone do not make a warm cabin. The genius is in how they are joined. Viking builders use scribe-fit joinery. Each log is individually shaped to fit perfectly against the one below it. A single wall might take weeks to fit properly. Why this trouble? Air. If wind can blow through gaps between logs, all the thermal mass in the world will not help. The scribe-fit method creates an almost airtight seal. When researchers test 18th-century Norwegian log homes, they find less air leakage than modern homes built to the strictest energy codes. The technique uses compression-fit notches, also called shrink-to-fit. As logs naturally dry and settle over the first few years, the weight above pushes the logs together. The notches are designed to close as logs shrink. What starts with small gaps becomes completely sealed, engineering that works with wood's nature, not against it. After logs are fitted, gaps are chinked with sphagnum moss, clay, and animal hair. Each component has a specific purpose. Sphagnum moss is nature's perfect insulation. Its cellular structure never truly dies. When dried in the wall, cells go dormant, but maintain integrity for hundreds of years. The moss remains springy, adjusting as logs move with seasonal changes. Each tiny sphagnum leaf holds 20 times its weight in water when fresh, but when dried, those structures trap thousands of microscopic air pockets. The R value of densely packed sphagnum approaches modern fiberglass. But there is more. Sphagnum is highly acidic, pH around 4. Bacteria and fungi that cause rot cannot survive. Insects avoid it. Finnish builders call it sina sammal, wall moss. It insulates, seals, flexes with movement, and actively resists decay, all at once, and it is free. The clay creates an airtight seal while moss provides resilience. Animal hair acts as binding fiber like rebar in concrete. This three-part system breathes, allowing moisture vapor to escape while blocking airflow. Viking cabins use logs 10, 12, even 16 inches in diameter. This creates thermal lag, the time heat takes to move through a material. A thick wall of dense wood can have a thermal lag of 12 to 24 hours. Even as outside temperature drops dramatically at night, the inside face of that log wall still radiates warmth it absorbed during the day. The cold does not reach the interior for many hours. By then you light another fire. The cabin becomes a thermal flywheel. A National Bureau of Standards study from 1980 to 1982 confirms this. Two identical structures, one with 7-inch logs rated R10, another with conventional framing at R12. During winter, both use similar energy, but during spring heating, the log building uses 46% less energy. Thermal mass becomes increasingly valuable as temperatures fluctuate. Section 3. The heating strategy. The Viking log cabin is designed around a single central heating source, the masonry heater. This is not a fireplace. Fireplaces pull massive amounts of heated room air up the chimney. A roaring fire in a traditional fireplace can actually make a room colder. The masonry heater is different. It is a massive structure, often weighing several tons, built from stone or brick. In Russia, they call it a pechka. In Scandinavia, a kakalugan. In Germany, a kakalofen. You build a hot, fast fire once or twice daily, but instead of venting straight up, smoke and hot gases route through a labyrinth of internal channels inside the masonry mass. These channels total 10 to 20 feet in length. As hot gases wind through this maze, they surrender almost all their heat to the stone or brick. By the time smoke exits, it is barely warm. All that heat is now stored in several tons of masonry. That mass radiates warmth gently and evenly for the next 12 to 24 hours. Surface temperature stays around 100 to 150 degrees Fahrenheit. Warm enough to feel wonderful, but not dangerous. A proper Russian stove weighs about 2 metric tons, 4,000 pounds of thermal mass. The internal maze of channels is called kolenya, meaning knees or bends. The fire brick holds 80% more heat than cast iron, while its heat conductivity is 1/45 that of steel. The brick absorbs heat rapidly but releases it slowly. An iron stove gets hot and cools fast. A masonry heater maintains warmth for an entire day. Mark Twain, visiting Russia in the 1800s, wrote about these stoves with amazement. A servant burns a small basket of thin pine sticks for 10 to 12 minutes in the morning. The door is then locked. The stove's surface is never too hot to touch, yet the room stays warm until past midnight, all from 12 minutes of fire. This is radiant heat. It heats objects and people directly, not the air. No hot ceiling and cold floor. The whole room feels evenly warm. Viking builders placed the heater in the center of the home, with the mass forming one wall of a sleeping alcove. At night you sleep with your back against warm stone. Some designs have baking ovens built into the structure or heated benches. In severe climates, people sleep on top of the stove, where the surface is warm but safe. In multi-room cabins, the heater is built as a shared wall between rooms, radiating heat in all directions. A brick flue in the attic sometimes includes a chamber for smoking food. And here is what modern homes miss. Thermal radiation works best in small, enclosed spaces. Viking cabins are not open-plan spaces. Rooms are compact. Ceilings are low, often just 7 feet. This keeps warm, radiant surfaces close to people. Finnish researchers reconstruct and test a traditional log cabin with a masonry heater. A single 2-hour firing using about 30 pounds of wood maintains 65 degrees for over 18 hours, even with outside temperature at -4 degrees. Total fuel consumption is 60 to 70% lower than conventional systems. The Viking system is not just more efficient, it is resilient. It does not depend on continuous fuel or electricity. If you cannot fire the stove for 3 days, the cabin stays above freezing. A modern home, uninhabitable in less than 24 hours. Section 4. The complete system, how it all works together. The Viking log cabin is not one clever trick. It is a complete integrated system where every element supports the others. The foundation uses stone piers, lifting the floor off cold ground. The floor is thick planks, sometimes doubled, with moss or sawdust insulation underneath. This breaks the thermal bridge to earth. The massive log walls provide both insulation and thermal mass. The scribe-fit joinery blocks air infiltration. The sphagnum moss chinking flexes with seasonal movement while maintaining an airtight seal. Low ceilings and compact rooms keep warm air close to people. The central masonry heater stores and radiates heat for hours. But there is one more element: thermal zoning. Viking cabins are not kept at the same temperature everywhere. The main living area might be 65 degrees. Sleeping areas might be 55 degrees. Storage areas are even colder. This is intentional. You do not need the same warmth when asleep under heavy blankets as when awake and working. By allowing thermal gradients, they reduce total heat load. Modern homes try to keep every room at the same temperature, requiring enormous energy. No heat escapes without providing benefit. The chimney passes through upper floors before exiting, warming those areas. The cooking area is adjacent to the heater, using waste heat. Bread is baked in ovens built into the masonry mass. Small spaces behind and under the stove, called zapechi and podpechi in Russian, serve as warm, dry storage. Boots dry there, clothes stay warm. These systems require knowledge to operate, but very little maintenance. The masonry heater needs cleaning once or twice yearly. Log walls need periodic inspection and rechinking. No filters, no motors, no electronic controls. A child can learn to fire a masonry heater properly in a single day. And these structures improve with age. As logs fully season in place over the first few years, they stabilize and seal even tighter. The masonry heater develops microcracks that actually improve heat distribution. A 50-year-old cabin is often warmer and more efficient than a new one. This is the opposite of modern construction, where buildings begin deteriorating the moment they are completed. Section 5. The modern disconnect. Why we abandoned what works. If these Viking systems are so effective, why do we abandon them? Three forces: industrialization, cheap energy, and changing labor costs. In the 1800s, as North America is being settled, there is a rush to build quickly. Scribe-fit log construction is slow and requires skilled labor. As sawmills become common, it is faster and cheaper to build stick-frame houses. These go up in weeks instead of months. Then comes cheap fossil fuels. In the early 1900s, coal is abundant and inexpensive. Later, oil and natural gas. When you can heat a poorly built house for just a few dollars a month, thermal efficiency becomes irrelevant. The post-World War II building boom accelerates this. Millions of homes are needed fast. The methods that become standard are optimized for speed and low initial cost, not for performance or longevity. But insulation without thermal mass creates the problem we have today. Homes entirely dependent on active heating systems. The average American home uses about 90 million BTUs for heating yearly. That Viking cabin, probably closer to 15 million BTUs, and it is more comfortable. Modern homes appear cheaper to build, but over a lifetime they are far more expensive to operate. A stick-frame home in a cold climate might spend $3,000 to $5,000 yearly on heating. Over 30 years, that is $90,000 to $150,000 yearly on heating. A well-built log structure with a masonry heater might cost more up front, but operating costs are a fraction. No furnace replacements every 15 years, no ductwork to maintain. The savings, compounded over decades, are massive. But modern construction is not optimized for life cycle cost. It is optimized for the lowest sale price to maximize profit margin. The skills required for scribe-fit joinery are not taught in trade schools. Knowledge of masonry heater construction exists in only a handful of practitioners. When the last generation that knew these methods dies, the knowledge dies with them. In rural Alaska, Russia, and parts of Scandinavia, people still live in cabins built this way. They burn a fraction of the fuel their neighbors burn. They are comfortable when power goes out. They simply maintain knowledge the rest of us have discarded. Section 6. The proof in practice. Does this actually work in the real world? Researchers have tested these principles, and the results are striking. In 2004, a University of Alaska team builds two identical small cabins. One uses modern methods, 2x6 framing with R19 insulation, vapor barrier, drywall, and a propane furnace. The second is a traditional log cabin with 10-inch logs, scribed joinery, and a masonry heater. Both are placed in Fairbanks, where winter temperatures regularly hit -40 degrees. They monitor both structures through an entire winter. The modern cabin requires continuous furnace operation to maintain 70 degrees. Daily propane consumption averages 18 pounds. When propane is shut off to simulate a power outage, interior temperature drops to 40 degrees in 8 hours, reaching outside temperature within 24 hours. The log cabin with the masonry heater is fired twice daily, using about 35 pounds of wood total. Interior temperatures range from 62 degrees before morning firing to 72 degrees an hour after. When the heater is not fired for 3 days, interior temperature only drops to 48 degrees. The thermal mass holds enough warmth to prevent freezing for over 72 hours. Occupants of the log cabin consistently rate their comfort higher, even when air temperature is sometimes lower. This is the effect of radiant heat. You feel warmer when surrounded by warm surfaces. The Norwegian Institute of Wood Technology tests historic log homes, some over 200 years old. These structures, when properly maintained, have lower heating costs and better comfort than new homes built to modern energy codes. Thermal imaging on cold winter nights shows modern homes with massive heat loss through windows, doors, and penetrations. Log homes show almost no hotspots. The entire thermal envelope is stable and even. The conclusion is consistent. Thermal mass, tight construction, and radiant heating create resilient, efficient structures that remain comfortable with minimal energy input. Most building codes are based on R value, measuring thermal resistance. A log wall with R10 does not meet code requirements in most jurisdictions. But R value only measures steady-state heat transfer. It completely ignores thermal mass. A log wall performs far better than its R value suggests because of its ability to store and release heat. Several states have exempted log homes from normal energy compliance because they recognize R value alone does not tell the full story. But most building codes remain stuck in a paradigm that cannot account for thermal mass. This is why a log home with inadequate insulation by code standards outperforms a modern home with R40 walls in real-world testing. If this investigation has opened your eyes to what is possible, hit that like button and subscribe. This knowledge, the wisdom of builders who actually have to survive without backup systems, needs to be preserved and shared. What we can learn. The secret to why Viking log cabins stay warm in brutal cold while modern homes freeze is not a single innovation, it is a complete understanding of thermal physics applied with materials that work with nature, not against it. Dense, old-growth timber providing thermal capacity. Scribe-fit joinery creating an airtight envelope. Sphagnum moss chinking that breathes, flexes, and resists decay. Masonry heaters storing heat and radiating it for hours, compact spaces keeping warmth close to people, strategic thermal zoning, every element working together. Modern construction has optimized for speed and initial cost, creating homes that are fragile, dependent, and expensive to operate. We trade resilience for convenience. We trade knowledge for simplicity. But the old methods have not disappeared. Builders in Scandinavia, Russia, and parts of North America still practice these techniques. The knowledge exists. What is missing is the will to use it. These Viking builders are not primitive, they are sophisticated engineers who understand their materials and environment deeply. They build for survival, not for profit. And what they create has outlasted and outperformed almost everything we build today. The numbers tell the story. A Viking cabin uses 15 million BTUs per year. A modern home uses 90 million. The cabin stays livable for days without heat. The modern home becomes dangerous in hours. The cabin improves with age. The modern home deteriorates from day one. This is not nostalgia. This is physics. Can these principles be applied to modern construction? Can we build homes today that combine the thermal resilience of a Viking cabin with the convenience we expect? The answer is yes, and there are builders doing exactly this. In the next investigation, we visit a modern home built using these forgotten principles. We see how it performs, what it costs, and whether this knowledge can be scaled. If you want to see that, make sure you are subscribed with notifications on, because if we are going to fix how we build, we need to start by understanding what actually works. Thank you for watching. If this has made you think differently about construction and heating, share it with someone who needs to see it. Let us know in the comments. Would you live in a home built this way? What keeps you from applying these principles? The Viking builders proved something important. You do not need high technology to create a warm, comfortable home in extreme cold. You need understanding. You need materials that work with physics. And you need the wisdom to build for the long term, not just for the sale. That wisdom still exists. We just have to choose to use it.